Today we're going to deal with air and carbonates. Now you might think the two things are totally random and not linked, but there is a link, and the main reason I'm doing it is because we include it in our Year 9 work. So let's start with air, and of course we all should understand air. It's the stuff we breathe, it's all around us. We should get to grips with what it is. So let's have a look. What is it? Well, main thing is air is a mixture. Look, mixture. And the big chunk of air, 78% nitrogen. Nitrogen gas, 78%. Green chunk, 21%, about a fifth oxygen. So if you think of air as being 4/5 nitrogen, 1/5 oxygen, can't go far wrong with that. Fair enough. However, a few finer points to put on top of all of that understanding. Argon. Argon, 1%. Argon. When you look at books and internet, they round these figures. So argon rounded is 1%. And that leaves carbon dioxide, 0.04%. I'll talk about that in a minute, but that's what I want you to learn. I want you to learn nitrogen 78%, oxygen 21%, argon 1%, carbon dioxide 0.04%. Now we could round the carbon dioxide to 0, but that would give you the wrong idea. We want you to know carbon dioxide is in the air. We want you to know a tiny percentage, 0.04%. Learn it. Now, when I first started teaching, I know it was a long time ago, 1985. Oh, that's too long to think about, really. Ago. Then this was 0.03%. And now I teach 0.04% because the percentage carbon dioxide in the air has gone up over my lifetime as a teacher. And you could try and quantify pollutants and water vapor, but they vary. So here we're talking about dry air with no pollutants. Dry air with no pollutants is a mixture, and it's these percentages. Dry air without pollutants. Now, when pollutants are present, depends where you are, what country you are, whereabouts, if you're next to a road or power station, then these will vary. But for dry, pure air without pollutants, these globally, these percentages are the same. So variable amounts of pollutants and water vapor exist on top of these percentages that we give you for pure dry air. Right, so one of my practical videos, I do this experiment, and you need to know about it. So if we start here with a gas syringe and we put in there 100 centimeters cubes of air, and we pass it over hot copper, then 100 centimeters cubes of air, when it goes over hot copper, the oxygen gas will react with the copper, making black copper oxide. This copper there goes black. As it does so, there's a reduction in volume. Less volume ends up in the other syringe, less than 100, because the oxygen is reacting away. And then you pass that remaining oxygen over the copper, back again, and you get less oxygen. And you pass it over again, keeping the copper hot, and you get less oxygen, 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 until there comes a point at which the volume of oxygen here, let me say that again, that's wrong. The volume of air left here, when you pass it over copper, it doesn't get less. The volume of air stays the same. Now, when the volume of air stays the same as you pass it over the hot copper, When the volume of air stays constant, then all the oxygen has been removed. And lo and behold, how much remaining air do we find? If we start with 100 centimetre cubes of air, we find that we're left with 79 centimetres cubed. Now, 79 centimetres cubed will mean that 21% is oxygen. 21% is oxygen. Look at my video if you don't believe me. Look at the video, I do the practical, and I am indeed left with 79 centimetres cubed when I start with 100 centimetres cubed. That 79 is 78 of nitrogen and 1 of argon. And 0.04% is carbon dioxide, but that's so tiny in our measuring cylinder we cannot measure it. So, experiment to show what percentage of air is oxygen. Common experiment, they ask about it on exams. You need to understand it, get your mind around it. I've just grabbed that image from the internet. So let's go over gases. Oxygen gas. Oxygen gas, the symbol is capital O. But whenever we have gas, now listen to me carefully, whenever we have oxygen gas, it's always O2. It's diatomic. 2 atoms of oxygen make a molecule. There are a double covalent bond between the oxygen atoms. These are 2 oxygen atoms. The green circle represents the encapsulation of that molecule. That is a molecule there, and that's how we write it there. Never write O unless you mean just the symbol for oxygen. The symbol for oxygen is not oxygen gas. Whenever it's oxygen gas, it's always O2. In the same way, whenever it's carbon dioxide and we've got carbon dioxide gas, it's always CO2. And the molecule is carbon with 2 oxygens, carbon dioxide. And there are double covalent bonds holding the carbon with each of the oxygens and so on. Nitrogen gas, and similarly, is N2. And in order to get full outermost energy levels, dot cross, 6 electrons need to be shared. 6 electrons being shared, 3 covalent bonds hold 2 nitrogen atoms together, and nitrogen atoms are diatomic. Now, argon is monatomic. Monatomic means single atoms on their own. So argon is made up of actual atoms. The symbol argon, Ar, is the same as the gas Ar. So Ar gas, Ar symbol are the same, but not for oxygen or nitrogen or fluorine, chlorine, bromine, iodine. None of them, because they are all, I might have referred to them earlier as the Super 7. Super 7 on your periodic table, find them. I'm talking about nitrogen, oxygen, fluorine across the top in groups 5, 6 and 7, nitrogen, oxygen, fluorine, and then coming down, fluorine, chlorine, bromine, iodine. Fluorine, chlorine, bromine, iodine come down. It makes a lovely 7 shape of those 6 elements. Together with hydrogen is diatomic. Those 7 are diatomic. And so many boys and pupils write those gases incorrectly. And of course, bromine and iodine, bromine is a liquid, iodine is a solid. They write them incorrectly with symbols, just their symbols, and it's wrong. That you need a little 2 to make it diatomic. You need a little 2 to make it diatomic. Don't forget that. So, in air, we have 21% oxygen, 0.04% carbon dioxide. How do we prove these gases? You need to know their tests. To prove oxygen, we relight a glowing splint. A glowing splint relights in oxygen. That's the proof of it. What's the proof of carbon dioxide? Well, when you shake it or bubble it with lime water, shaken or bubbled with lime water, if the lime water gives you a white precipitate, that that means that mixture starts looking white and you can't see through it, then that will be calcium carbonate there, and the calcium carbonate will be made only if carbon dioxide is present, and carbon dioxide being present gives you that white precipitate, and that is proof you got carbon dioxide gas. So using lime water in that way proves carbon dioxide. There's no test for nitrogen because nitrogen is inherently not reactive. Nitrogen not being reactive means that whatever we try and react it with, it doesn't do anything. So there's no simple chemical test for nitrogen. Equally with argon. Argon is your classic group 8, group 0 element, noble gas, inert gas that does not react. We cannot do a simple test to prove it's there. There's no such simple test available to us. So learn these two: carbon dioxide test, oxygen test. You already know the squeaky pop test for hydrogen, and there are others that will come across later like chlorine, etc. But I'll teach you those when the time comes. Let's move on. Next slide. Right, burning. Now, burning, combustion, is a reaction with oxygen. So you might call it, oh yes, such a thing's burning, or such a thing is combusting. As a chemistry person, I look at those things, all right, such and such a thing is reacting with oxygen. Indeed, without oxygen in our air, we wouldn't be able to burn things in air. Now, when we're burning things in the real world, it's always reaction with oxygen. Nitrogen doesn't react. Argon doesn't react. Nothing burns in carbon dioxide. Well, that's not quite true, actually, but I want you to think, nothing burns in carbon dioxide. It is only oxygen in the air. People talk about the oxygen in the air as being the reactive part of the air, which is why we get reactions with air. It's always the oxygen. The oxygen makes burning possible. The oxygen makes rusting of iron possible. It is always the oxygen that reacts. The oxygen reacts with aluminium and makes a layer of aluminium oxide around the outside of aluminium, protecting it, which is why we make aluminium windows, etc. So learn those things about burning. If elements burn, they're going to join with oxygen. If compounds burn, then they're going to join with oxygen. It's the elements within the compound that will join with the oxygen. Whatever you think about, burning and combustion are joining with oxygen from the air. Now, during burning, some of the oxides that you get are pollutants, and these pollutants end up in our air. So say you've got sulfur. If you burn coal, 1% of coal is sulfur. If you burn it, then you get some sulfur dioxide, sulfur oxides. Say you've got protein. Say you've got like a lump of meat. You burn the lump of meat. Any nitrogen in that lump of meat will end up making nitrogen oxides. Now, sulfur oxides and nitrogen oxides, they cause acid rain. And acid rain is a phenomena that you need to know about for GCSE. Carbon dioxide gives you global warming. Now, I need to get into these ideas. I need to get into ideas of acid rain and global warming, and I need you to understand them. So let's deal with acid rain. Acid rain comes about when we have nitrogen oxides and sulfur oxides. So things have got nitrogen in them, like proteins. Things have got sulfur in them, like living things. 1% of living things are typically sulfur. When you burn them, the nitrogen makes nitrogen oxides, and there are about 6 of those. So various nitrogen oxides are formed, and often you get sulfur dioxide with the sulfur that's present. Now, both of those oxides, nitrogen oxides and sulfur oxides, will dissolve in rain. So say it rains, and these gases are in air. Nitrogen oxides, sulfur oxides are in air. If they're in air and it rains, the rain goes through the air, the nitrogen oxides, the sulfur oxides will dissolve into the raindrops. When they dissolve into the raindrops, nitric acid or sulfurous acid is made within the raindrops. Now, you don't need to know the names. You need to know that when these gases dissolve in raindrops, the raindrops come down as slightly acidic. If you test them with a pH paper, I get a pH of about 6. Now, 6 is less than 7. Anything less than 7 is acidic. So they're acidic, okay. I agree with you, weak acids, they're weakly acidic, but they're acidic nevertheless. And the acidic rain, when it comes down, will mess up crops for farmers, will mess up great buildings like the Taj Mahal that's made of marble, because acids react with marble, giving a fizzing reaction. So buildings react away, crops are not as plentiful as they would have been. Acid rain can be a problem. And basically you've got to know about it. So I hope you understand how it comes about, acid rain, and learn some downsides to it. The downsides are that crops are reduced by acid rain, and buildings, some buildings, marble buildings, are reacted away by acid rain. Right, greenhouse effect. Now, this is a little bit harder to understand, but I'm going to try and explain it to you. When you have sunlight from the sun, look, sunlight here, sunlight coming in, the sunlight comes into our Earth through the atmosphere, and its frequency of light is ultraviolet. It's ultraviolet light, UV light. Now, if you go to a nightclub or disco where your white shirt stands out and is glaringly obvious, then that's because nightclubs and discos use ultraviolet lights. And white things will will reflect. White clothing will reflect ultraviolet light, and you see it and it stands out. And it's an effect that everyone, I hope, is familiar with. So I want you to think that sunlight comes from the sun, down, hits our Earth, and it's ultraviolet light. That's fine. It will bounce off our Earth. And when it bounces off Earth, the reflected light changes frequency. The reflected light goes lower in frequency. Instead of it being the ultraviolet region of the electromagnetic spectrum, it won't be ultraviolet light anymore. When it's reflected, its frequency goes down and is reflected as infrared light. IR, light, infrared light. Now, infrared light is lower frequency. When that infrared light starts to reflect off our Earth back out into outer space, then molecules like carbon dioxide, molecules like that, like methane, chlorofluorocarbons, those molecules will absorb, and they do absorb, even water vapor does absorb infrared light. When that infrared light gets absorbed, rather than it going out and going to outer space, instead it gets absorbed and it stays in our atmosphere. And our atmosphere gets warmer. And when our atmosphere gets warmer, our Earth starts to warm up. Our Earth starts to warm up in that greenhouse effect way. And why do we call it the greenhouse effect? Well, it's similar to why a greenhouse, inside the greenhouse, is warmer. The sunlight comes in, the glass reflects some of it back in, and the inside of the greenhouse stays warmer than the outside of the greenhouse, where you've got free ventilation, etc. It's that kind of effect. Ultraviolet light comes in, the infrared light, not all of it manages to escape again, because molecules, greenhouse gas molecules like methane, carbon dioxide, those kind of molecules water vapor, those molecules will absorb infrared light and will keep some of that in our atmosphere and make our atmosphere warmer, and our Earth warms up. Another effect, another name for all of this is climate change. Climate change. Our climate seems to get warmer. It's not just about warmth though. It's about extremes of climate. Our climate is getting warmer, but it gives us extremes. We find many more storms nowadays than when I was a lad, and we find that places that I grew up in, like Pakistan, that were once fertile are now deserts, because the few degrees increase means those fertile areas are no longer fertile, they're deserts. And when I came to England as a 6-year-old lad, I used to see snow every winter, and now we're lucky to get snow every now and again. I've not been sledging for a few years with my grandkids because we haven't had any snow for a few years. But yeah, I suppose I'm rambling. I'm sorry. Look, you need to know about the greenhouse effect. You need to know about climate change. Really important subject for human beings on our Earth. We live on our Earth. You should make an effort to understand it and why it's getting warmer, why climate change is such a big topic, because it will affect many people, not just in terms of climates getting warmer, but the ice caps, North and South Poles melting away, sea levels rising, extremes of climate. These things are some things that my children, my grandchildren are going to have to deal with, and I feel sorry for them because what do you do? I do my bit, but it's a drop in the ocean. I drive an electric car. What do? I have solar panels. Drop in the ocean. Sorry, I do waffle from time to time. Let's go. Right. Now, I don't think directly the lab prep of oxygen is in the AQA syllabus, but I want you to know about it. I want you to do it. I want you to make oxygen. I want you to play with oxygen. I want you to look at the properties of oxygen, and you would do it like this. You would put hydrogen peroxide into a flask with solid manganese dioxide catalyst. Now, catalyst, what is a catalyst? Catalysts speed up reactions, but they are themselves unchanged at the end of that reaction. So, say you put in 1.27 grams of manganese oxide, black powder. At the end of the experiment, there must be somewhere 1.27 grams of manganese oxide, black powder. So catalysts at the end are exactly there in the same quantity that we started with. If they react away, then they're reactants, then they're not catalysts. Catalysts don't react away. Catalysts either react temporarily and are regenerated, or never react away and just help the reaction to undergo in some other way. Anyway, that's the apparatus. I do have a video, the lab prep and properties of oxygen that I've done, but if you're short on time, don't watch it. It's not in the AQA syllabus. Sorry, not AQA. It's not in the Edexcel International GCSE syllabus. That's the one we do. Edexcel International GCSE syllabus. It's not in that. It's been taken out, and MGS boys won't find it in their booklets because it's not there anymore. So, what's the reaction? The reaction I want you to know as well as the apparatus setup. I want you to know hydrogen peroxide. Now, hydrogen peroxide might look a bit like water. The formula looks a bit like water, H2O2, but crucially, it's not water. I once put my hand into hydrogen peroxide solution. Pulled my hand out, and oh my God, the hand was white. It was horrible. It was like a nightmare. I'd gone white by putting my hand in hydrogen peroxide. Luckily, it was temporary. After like 1 hour, my colour pigment in my skin regenerated and the colour came back to my hand. But peroxide is used to bleach hair. Well, I haven't got much hair, but if you go and get your hair bleached and want it to be white or lighter, then they would use hydrogen peroxide. It's a famous bleach. In chemistry, it's a famous oxidizing agent because it's got an extra oxygen. Look, H2O2. That extra oxygen makes it an oxidizing agent because that oxygen can be lost. Now, to lose the oxygen, you use a catalyst, manganese 4 oxide. The formula, MnO2, that's that black powder I was talking to you about. You put the black powder in the flask and then you add the hydrogen peroxide through the funnel and it bubbles and it makes oxygen. Let's go back. See? Hydrogen peroxide, manganese 4 oxide, and it bubbles, and the bubbles, that's oxygen there. So you get oxygen gas, look, and the hydrogen peroxide molecules turn into water molecules. So the hydrogen peroxide starts off being this fairly nasty chemical and ends up as water once it's given up the extra oxygen that it had to begin with. And we use that reaction, and that reaction uses that catalyst. Catalysts help to speed up reactions, but are themselves unchanged at the end of the reaction. So, know these things. The reaction is a catalytic decomposition. Decomposition means the hydrogen peroxide breaks down, so that's decomposition. Catalytic decomposition means it breaks down when a catalyst helps it to break down. The chemical hydrogen peroxide decomposes to make water and oxygen gas. The catalyst which helps this to happen is manganese 4 oxide, which is a black powder. Right, now, cod sliptum. You need to know those properties for oxygen gas. Colourless, odourless, density a little bit more than air density. Solubility does dissolve in water. Litmus, neutral gas. Inflammability does not burn, but things burn very well within it. Now, does not burn. Does not burn. Don't you dare in an exam write it burns. It doesn't burn. Things burn very well in it. So if I have an oxygen gas tank, like I do in fact, I have an oxygen gas tank in my bedroom, and I have to be really careful when using it because I know that if fires are much more likely in my bedroom because of that oxygen tank and the oxygen that I use it for breathing. It controls cluster headache, which I suffer from sadly, and you need to be clear that things burn very well within it, but the gas is not burning. If my bedroom catches fire, it will be the carpet and the bed and my clothes and those things that catch fire. It won't be the oxygen that's catching fire. The oxygen is helping them to catch fire. Is it poisonous? No, it's not poisonous. What's the test? It relights a glowing splint. Uses, I want you to learn it's used to make iron from iron ore. That's a safe use. I do not want you to write things like this, that we need oxygen to live. Uses in chemistry, when an examiner asks for uses, I want you to come out with some non-quibbleable, no-quibble use. Like, it's used to get iron from iron ore. I don't want you to say that it's used for breathing. That's not an industrial use, it's a life process. We need it for breathing, we need it for respiration. So there are some uses I tell you to learn, that's one of them, learn it. And I want you to know the end for notes. It's vital for living things to breathe, in like human beings, because when we breathe it in, we use it to carry out a process called respiration. And respiration in your body is what gives people, animals, plants, it gives them the energy to move. You need respiration to get energy to move from food. So those properties. Now that's oxygen. You need to know the same things for carbon dioxide. And again, it's not in the EdXL International GCSE syllabus. It's in many syllabuses, but not ours, sadly. But I would want you to know it. I would want you to do it. I would want you to get to grips with how we do it and what it means and the Cod-Slipton properties, etc. Right, so same diagram, same apparatus. Actually, the diagram is two-dimensional. That last diagram was three-dimensional. Look, three-dimensional diagram. Three-dimensional diagram, and this diagram is exactly the same in 2 dimensions. You have a flask, you pour the stuff in there, but this time the stuff we use is hydrochloric acid. Hydrochloric acid goes in, it reacts with marble chips. You put marble chips in the flask, the two fizz together, this is a long tube, and then the fizzing makes bubbles of carbon dioxide which you can collect. And I use test tubes to do the collection. Now whenever you collect like this, in a trough of water like that, then we say the phrase to use is the gas is collected over water. Now there are 2 ways to collect carbon dioxide gas. One, you can collect it over water, but you lose the gas. Some of it dissolves. Carbon dioxide is a soluble gas, it dissolves in water. So you're going to lose some of it as it bubbles into the trough of water, but then you can make so much that, all right, so what, you lose it. You lose some of it, you're going to get some, and the test tubes you have managed to fill will be full of carbon dioxide and you can test them. So it's no great loss, the fact that you've lost it. However, if you don't want to lose any, then you would do what we call a downward displacement. You would get you get a flask here, and you collect the carbon dioxide going down into your flask. And carbon dioxide is a heavy gas, so if it goes down, it'll push out the air. So it will displace air in an empty flask downward displacement of air, which you can do instead of having to bubble it through water. I like bubbling through water because you can see it. So what reaction makes carbon dioxide? Well, the reaction is this one. Calcium carbonate with acid makes salt, water, carbon dioxide. The general pattern is acid plus carbonate always makes some kind of salt. This is the salt, calcium chloride, water, carbon dioxide. You get calcium chloride salt because calcium, the metal, replaces the hydrogen in the formula of an acid. The acid is HCl. The calcium comes, pushes out the hydrogen, takes its place. So the salt is calcium chloride. Now, marble is what we put into the flask. Marble is calcium carbonate. Limestone is another form of calcium carbonate. Indeed, limestone is a sedimentary form and marble is the metamorphic form of the same rock. And that calcium carbonate is this here, marble chips. You add acid through the flask, it bubbles, the carbon dioxide gas is what we collect, and we form, staying in the flask, calcium chloride and water as a mixture stays inside the flask. The carbon dioxide collected in that way, we say, is collected over water. I think I mentioned that already. So, Cod-Slipton properties. Colourless, odourless, density. Now, density, much more dense than air. Solubility, dissolves very, very well in water. Litmus, it's an acid gas, it's an acidic gas. Inflammability, no. Things don't burn in it and it does not burn. Poisonous, no, not poisonous. Of course, if you just breathe it in, you're going to die. But that's through lack of oxygen. It's not the carbon dioxide that kills you. It's a lack of oxygen that will kill you if you only breathe in carbon dioxide. So get it right. Poisonous things are things that will harm you directly and do harm directly, not indirectly through depriving you of oxygen, etc. Test, well, shake it with lime water and look for a white precipitate or a milky coloration. Uses, it's used to make fizzy drinks and fire extinguishers. Notes, plants use it to carry out photosynthesis. Again, I don't want you to say plants use it to carry out photosynthesis. I don't want you to say that as a use for carbon dioxide. I just want you to know that. The use is carbonated drinks, fizzy drinks, or in fire extinguishers. It's used to put out fires. Now, I think I've been wittering on for 35 minutes. I think I'm going to stop there and then I'm going to carry on talking about carbonates. Let's see what the next slide is. Is it carbonates? Test for carbonate. Let's do this before I leave it. So, test for carbon dioxide. Lime water with carbon dioxide gives you a white coloration and water. Now, the white coloration is a white solid being made. So, when a white solid is made, what is that? Well, let's have a look. Lime water is calcium hydroxide solution. And that's lime water solution with carbon dioxide gas. It makes calcium carbonate. Now that is limestone or marble chips chemical. It's a white solid is what I'm trying to get to. So white solid is being made in that reaction. It's that white solid, the calcium carbonate, that makes your test tube look white and makes your test tube, I want you to say, white precipitate. White precipitate means solid made in the reaction. It's best to say you see a white precipitate. Don't say the word cloudy, because clouds can be grey. It's never grey. White precipitate or milky appearance, not cloudy. Right, so that's the end of the video to here, 37 minutes. I'm going to stop it and I'm going to record the next one about carbonate straight after, just to break it up into a more manageable size that fits into lessons.